And of course, there are 2 more talks on non-adiabatic molecular dynamics in this symposium. But what we do is different from what, for example, Maria Barbati does or Xingan Lan does. And that's why I'm going to start by talking a little bit about exactly how we do non-adiabatic molecular dynamics, because we developed methodologies that are particularly designed to study materials. And there are 2 approximations that we use that probably are not going to be very good for molecules, but they're actually very good for materials. And then I'll give you examples of how we use machine learning. So the simplest example is just to study a large system and long timescales and to be able to see rare events with the machine learning force fields. And this is usually done in collaboration with people who develop machine learning force fields. But what we do in our group, we now use various techniques of unsupervised learning to analyze data, because these new types of materials give interesting experimental results that are hard to understand, and machine learning help us to understand them. And more recently, we are now using, we're predicting or interpolating non-adiabatic Hamiltonian with machine learning, and we hope to be able to run an AMD that are not just a few picoseconds at the initial level that we are doing right now, but hundreds of picoseconds, maybe nanoseconds, and I'll give you some examples of that. So what we're doing is non-adiabatic molecular dynamics. Electrons are quantum mechanical, nuclei are classical, and we're interested to include transitions between electronic states. And usually we have materials such as 2D materials or Perovskites, something that has pretty large, they have many atoms usually, and they have defects, and you have interfaces of those materials with other materials to study charge transfer and energy transfer. So they actually mostly come from physics than from chemistry. And because of that, we use DFT, which is a very good way to describe properties of such materials. What we do time-dependent Conchem theory. And so this is all standard stuff that was done by Hardy-Gross a long time ago. The way we solve time-dependent Conchem equations was by using adiabatic Conchem orbitals that we take from many DFT codes that are available. And we expand the time-dependent Conchem orbitals in these adiabatic Conchem orbitals, and then we get equations for the coefficients of the expansion, and these equations contain this non-adiabatic coupling that we need to evaluate. When we started to do this way back, we actually did Ehrenfest dynamics, right? So there are different ways you can do non-adiabatic dynamics, and Ehrenfest is the most rigorous way, at least you can derive it, and it's the easiest way, I would say. But it had its own problems. And we started to do it using this adiabatic representation, Conchem representation, which was different from what people in the physics did. Usually they used some numerical grids, gave some advantages, disadvantages, but at that point it was just a way to propagate time-dependent Conchem equations. But as I'll show on the next slide, there are several reasons why we have to do surface hopping. The surface hopping, we have to define states. And the Conchem basis gave us a simple way to define zeroth order states between which we can hop. When surface hopping was introduced, it was introduced to achieve branching. So it was done back in 1971 by Tully. And he argued that if you have an atom that scatters from a surface, it can scatter elastically or inelastically, but average Ehrenfest mean field way of propagating the atom is going to give unphysical results. And that's how he introduced surface hopping. But for us, that's not the issue, actually. The issue is that Ehrenfest has 2 other problems. For example, Ehrenfest method cannot properly transfer energy from quantum electrons to classical atoms. And if we want to study charge trapping or charge recombination or energy transfer, charge separation, which always compete with energy losses to heat and involve electron-phonon coupling and energy losses to heat, we cannot do this with Ehrenfest. But surface hopping, and that's how we started to do surface hopping, because Tully showed it right before we published this paper, can achieve detailed balance. It can achieve equilibrium in the long time limit. And the second issue is decoherence. When you're looking at scattering events like this one or isomerizations of molecules, transitions are usually local. But in our models, transitions happen over long time scales, nanoseconds. And in that case, we have to include this effect that's a purely quantum mechanical, quantum dynamics effect, such that quantum vibrations have induced loss of coherence in the electronic subsystem. And Ehrenfest method was not designed to do that either. So it's because of these 2 things that we started to do surface hopping. And we'll look at it more like a master equation, really, than propagating on excited state surfaces, because our methodologies they tie on one end to molecular simulations, but on the other end to people that study materials, and they do various kinds of master equations in which you have rates that are time independent, more simplistic descriptions. For us, surface hopping is like a master equation, but with rates that are explicitly dependent on time, dependent on configuration of the atoms, and so on. Often we have to deal with huge dimensionalities. For example, we had a couple of papers 10 years ago where we had to study its multiple exciton generation in quantum dots, which was a very important topic for a long time. And then it evolved into singlet fission, for example. And even in a small quantum dot like this, we had to deal with hundreds of thousands of states, almost 100,000 states, and then later more states. And this representation, Concham representation, many-body Halide determinants made of Concham orbitals, give us very sparse non-adiabatic matrix elements, and we could evolve Chern equation in hundreds of thousands of dimensions. But also we have to include Coulomb interactions, which is often done in linear response to DDFT, for example, and then you solve Casida equations to get a better description of excited states. Or in physics, this is done through Bader-Salpeter equation that is built on top of GW approximation. And so we do the same. We evaluate Coulomb matrix elements, but we're not trying to solve for eigenstates in the linear response to DDFT sense, because there are lots of states. What we do, we include those matrix elements as off-diagonal matrix elements together with non-adiabatic couplings, and then we still solve the Chern equation in the Concham basis. But this way we can describe energy exchange between electrons and holes, and this is important also in many nanoscale systems. So this is classic example in a quantum dot where electron goes from P to S-like state and gives energy to the hole, and this breaks the so-called Phonon bottleneck. So the approximation that we use works for nanoscale systems because they don't have any complicated geometric deformations. So in a molecule, you excite one electron and it can isomerize, bonds can break, and so on. But in our case, mostly things just vibrate. And for example, if we compare Concham excitations based on with linear response, DDFT excitations for a quantum dot, typical material we study, which has some surface passivation and so on, there's no difference if you just look, the gaps are the same. And then if you look at the excited states, and this is just random piece of trajectory, excited state energies are the same. So this description is very good for nanoscale systems. And then additional terms like Coulomb terms we treat on top of that. So, so this is important for how we do our simulations. We make this classical path approximation, which has two steps. One step, we assume that the DFT functional that is still used, that's used to evolve the true density, depends on the ground state density only. Because in normal real-time TDDFT, you update your density every electronic time step, which is attosecond time scale. And then you have to calculate new DFT functional for the new density and update everything every maybe 10 attoseconds. But for us, because we assume excitation of 1 or 2 electrons does not change the density of electrons of a material that involves hundreds of electrons, we can make this approximation. And this way we can save recalculating the DFT functional. We do it on a nuclear time step, not electronic time step. And the second is that we assume that excited state trajectory is very similar to ground state trajectory because it's usually driven by fluctuations. There are examples when we do use excited state forces. For example, we do constrained DFT. We did this for methanol dissociation on TiO2 and other examples. But in majority of cases, what matters are thermal fluctuations. And in this case, we can use long ground state trajectory, compute non-adiabatic couplings along the trajectory, and then evolve quantum dynamics. So the density evolves, the populations evolve, but the trajectory is still the ground state trajectory. So we've done this. Alexei Akimov, who's now a professor in Buffalo, he wrote this code. Now he continues to develop it. If you want to use what we do, you should look at his webpage. So we include all sorts of interaction: electron vibrational, electron-electron, spin-orbit interactions. It gives you non-perturbative description of all those interactions, configuration dependent. And there are many codes with which now it's interfaced. Let me now explain how we started to use machine learning in our simulations. So in the first little examples, I'll show you how we can sample rare events that make a difference for important materials applications. In the first case, we collaborated with Wissam Saidi, who develops machine learning force fields. And what he's done, he developed a force field for a metallic particle on the surface of a 2D material. And this is a very important type of system because of plasmonic applications and also of catalysis. People use plasmonic excitation to excite, to put energy into metallic particles. And then there's lots of debate in literature, including experimental groups in Shaman. People debate whether the reaction that happens once you photoexcite plasmon in a metallic particle happens just because of heating. Energy goes very fast to heat because it's a metal, everything relaxes very fast, or excited states matter. Also, metallic particles are used for catalysis, and catalysis usually happens at some defects or maybe edges or apexes of these particles. But this is also important. But what we've done in this case, we use this machine learning force field, and we obtained long trajectory, several hundred picosecond trajectory, and we saw this top atom of the pyramid is shifted. But this happens on a pretty slow time scale, maybe 50 picosecond time scale or 100 picosecond time scale. So it's hard to do this with ab initio. But once it's shifted, the lifetime of the electron increases, and it's increasing maybe not by too much, factor of 2.5, but it can actually matter for some photochemistry, because if you have a molecule absorbed on this particle, and then you have hot electron that does not decay for almost a picosecond, it have enough time to start breaking some bond. So 100 femtoseconds versus picosecond could make a difference for some photochemistry. This was one example. Another example, so this paper is collaboration with Limin Liu, who is in Beihang University. This was not machine learning, but we're following up on this one. But it gives you another important example why machine learning force fields and rare events are important. So this is now metal halide perovskites, a very, very popular topic. They're very good for solar energy materials, for optoelectronic applications. And one of the main features is that defects in these materials are not so bad. And people say, oh, okay, you can have a halide vacancy, so you can have iodine missing, which is the most common defect. But for the reasons of the electronic structure of this material, because of lead to a large extent, this defect creates no trap state. So it creates a defect state inside the conduction band, but it creates no mid-gap state. But it's very well known that in these materials, especially if you have electric fields present, solar cell, for example, these defects can migrate. And what we've learned that if this defect migrates, you have a vacancy, moves from one place to another place, then this trap state goes into the gap. So this defect state used to be inside the band, have no contribution for the relaxation of electrons and losses of charges and performance of solar cells. But if you have defects migrating, if you apply some electric field, you shine light, you have all these processes happening, then the lifetime is going to decrease tenfold. And therefore, whatever people study by doing electronic structure calculations for optimized structures, or even room temperature, but not allowing defect migration, may not be relevant for real operating conditions when solar cells are functioning. But then what we also do, we use unsupervised learning to analyze data. And also we use it to develop simplified machine learning models for non-adiabatic Hamiltonians that we use, which follows to the leads us to the last topic. So here's a couple of examples of this kind of analysis. So for example, again, the same metal halide perovskite. What was shown experimentally in this and other papers is that the lifetime of excited state increases as you increase temperature. And this was very, very strange, because usually when you freeze something, electron vibrational interaction is very small. Non-adiabatic coupling is zero at zero temperature, or when the velocity is small at low temperature, it's small. And because of that, lifetime usually becomes longer at low temperature and shorter at high temperature. But solar cells are usually heated up. So the fact that lifetimes becomes longer at high temperature is very useful for solar cells. And this is what people see in experiments. And this is what we saw in the calculation, which was quite surprising for us, because the non-adiabatic coupling should be larger at high temperature because velocity is larger, but it came out to be smaller. Why? Because it's not just velocity, it's this matrix element that also matters. When we look at charge densities, we see that at high temperature, you create some kind of disorder. And because of disorder, you have some localization of electron and hole in different parts of perovskite. it's a small disorder and modest localization, so charges still move. But because of this partial localization, we have this matrix element becomes smaller, and even though velocity becomes larger, overall coupling becomes smaller and lifetime becomes longer. So once we started doing machine learning, we looked at this issue, and what we've done was very simple. We just computed mutual information, figure out what's more important in this perovskite for the non-adiabatic coupling, basically, and for the charge carrier lifetime and for the band gap. Is it motion or is it geometry? And if it's geometry or motion, what kind of geometry and what kind of motion? So first we found that the most important features, and these are just simple angles or bond lengths or rotations of bonds, or motions of angles or bonds, also rotations of MA, because it's a molecule that can rotate inside perovskite. We find that geometry is more important than motion. So this confirmed the fact that if you look at the matrix element, it's not the velocity that matters, it's the structure that determines the overlap of the HOMO-LUMO, basically. What also is interesting is that we identified this angle, iodine angle, that is has the highest correlation with the non-adiabatic coupling and with the band gap. But people in this field usually talk about iodine angle. So we identified a new angle that's even more important. And also we found that this cation MA, which is it's spectator, it does not contribute to conduction band, to valence band, HOMO-LUMO. HOMO-LUMO are localized on iodines and leads, even though it contributes nothing to the electronic states, contribute nothing to the wave functions, and therefore they don't contribute to the non-adiabatic coupling matrix element. They still contribute, they still influence it, although it could be either steric effect or could be through electrostatic interaction, because MA has asymmetric charge density distribution. And so just now, Wei-Bin Hao, who is actually an undergraduate student in Singapore, I have an experimental collaborator there, and that's how we connected. I'm supervising his diploma or master's or whatever project it is that he has to defend. In the modern days, it's easy. And he's going to do some collaboration with the Alexander Tkachenko in January. So what he's done, he's analyzed in more detail various features, right? So we want to construct models for non-adiabatic Hamiltonian, and we use the standard descriptors that come from the force fields back from the work of Farinello, and Alexander Isaev also developed on those as well. So what we first did, we used all descriptors the way people use force fields, and then we computed non-adiabatic coupling. And then we realized that we actually can reduce the model. What we've done was to use either cesium lattice or lead lattice or iodine lattice. And for iodines, because we have 3 times more iodines, we used every third iodine. The number of elements in all 3 cases is the same. The number of parameters is the same. And what we discovered, first of all, that even if we use just descriptors only for every third iodine, that's already giving us a good representation of non-adiabatic coupling and band gap. So this is coupling, this is band gap, almost as good as the full description. So we can use reduced simpler model. What we also discovered is that lead is really bad, which is strange because lead contributes both to HOMO and LUMO, but lead is much, much worse than iodine with the same kind of descriptors. And what we also found is that cesium, which just like before MA, does not contribute to HOMO-LUMO, it still gives you a good description. So cesium works better than lead, but iodine is enough, and not even every iodine. We can build good models with just every third iodine. And then we also looked at individual features, because in this case, we have several features associated with each atom. And we analyzed and we discovered that if we focus on iodine, we can just select one feature of iodine, which would be so the angle and the distance would be iodine cesium distance, and then lead iodine angle, or iodine cesium distance and iodine angle, almost the same result. Even a single feature, it's an iodine, can give us very good description of non-adiabatic coupling and band gap for this material. So the last couple of minutes I'll spend on showing how we accelerate NAMD. The main idea is the following. It's in this sentence. We don't want to build models of non-adiabatic coupling and excited state energies the way people build models for force fields, because it's very consuming and expensive. You need many electronic structure calculations, and excited state forces more complicated typically than ground state forces. Non-adiabatic coupling, it's also even more complicated, has more complex dependence on geometry. Moreover, the number of non-adiabatic coupling scales as number of states squared. So it's really, really hard to try to do this, although we tried. But then we realized, oh, we're using classical path approximation, which means that we can pre-compute trajectory. And therefore, we are using machine learning force field to pre-compute trajectory. But then we sample non-adiabatic coupling ab initio only along the trajectory. And I'm showing you, we've done this several systems. I'm showing you example where we have defect state, trap state. So in this case, one of the cesiums is replaced with this red little iodine here. So we want to know how fast charges are trapped by this defect, and then does this defect accelerate charge recombination or not? And we're able to get very good results with just sampling non-adiabatic coupling. In this case, there are 3 couplings and one, and this is pristine system, and this the same similar information from the band gap also I'm not showing. So we're able to sample initio only 2% of points along the trajectory. So if we run 7 picosecond long trajectory, we only need so 1% is what, 70 points, 140 points of ab initio data to be able to get good results. And this is the results I'm showing you. So we 4% sampling, 8% sampling give comparable results. Going beyond 2%, below 2%, you see some deterioration of the data. This is pristine system comparison of a full ab initio and this machine learning model of the Hamiltonian, and this is with the trap state. So the results are very good. What we're doing now, so this is one of the examples I showed you before, that we know that when we have a vacancy, if it starts moving, it creates a mid-gap state. What we've done using machine learning force field from Wissam Saidi, we ran nanosecond long MD, and then we see, so this is distance between 2 LEDs, because when you're missing iodine, if this atom is missing, these 2 LEDs can come together. And once this distance between 2 LEDs becomes small, we can see not just 1 mid-gap state, but up to 3 mid-gap states. So what we're doing now that we can only use, we don't need to use more than 2% of ab initio data to get the coupling, we can sample NAC from this trajectory, and we can do 3 picosecond, 200 picosecond, maybe even more, an AMD that samples all these unusual events, and it's going to be much more realistic description of excited state dynamics in Perovskites in this case. And this is something that we couldn't do before, so hopefully soon we'll be able to produce results for that. And so all this stuff is very new, and many of it is not published yet. So to summarize, what we do, we developed for a long time a branch of non-adiabatic molecular dynamics that is very suitable for nanoscale materials. And because we use materials and we compete with people in physics, we use DFT, band structure, basically to describe electronic states. And then if we need some exciton effects, things like that, we put them on top of the band structure. So we did it using TDDFT type matrix elements, and Jin Zhao, for example, with whom we also collaborate in Hefei, she did it using beta salpeter, but it's based on quantum theory with extra stuff. Then what was really essential for application of machine learning, we use this classical path approximation, because in many, many cases, we see the thermal fluctuations, rotations of some MA molecule in perovskite. Those fluctuations are more important than differences in the geometries induced by photoexcitation. And what we do, we can sample rare events using machine learning force fields, and then we can discover interesting things about data that come out from an AMD using unsupervised learning. And then now we are working to be able to do an AMD on hundreds of picosecond or nanosecond timescales, because we can interpolate the Hamiltonian instead of extrapolating. Instead of predicting a Hamiltonian into the future of the trajectory, we pre-compute trajectory, then sample along the trajectory just 2% of the points, and then this is enough to get a high quality NAMD Hamiltonian and run the simulations. I'm going to stop, and thank you once again for the opportunity to present and learn more about machine learning. Thank you.